Okay, hello everyone. Today we are starting with a new topic. The topic is the electric field as a gradient of electric potential, or we can simply say that we have to find out the relation between electric field intensity and V. That means V means the potential difference. That means we have to find out the relation between E and V. Now for this, what we have done, we have taken a charge plus q. This is the charge plus q, and the electric field is created because of this plus q. Say the direction of the electric field is away from plus q. Now let us suppose we are having another charge plus q0, and what we are doing, we are moving this charge from point B to point A. We are moving this charge from point B to point A. Now when it's enter inside the electric field created by a plus q charge, then what happen? It's it's experienced a force, that is F equals to E q0. So it's experienced a force F equals to E q0, and we know that work done dw equals to force into displacement. Displacement is how much? Displacement is dr, that is from B to A. The displacement is dr, so that means work done, when we calculate work done, the work done equals to F into dr. So this we have done. So put the value of F. The F will be E minus q0 minus sign indicate that the force is in the opposite direction of movement. So we have put it the value. Now what we are doing, we are just bring this q0 here. Now dw upon q0 is what? Dw upon q0 is your potential difference. So in place of this we are writing dv. So dv equals to minus edr. So from here we can calculate the value of E. This is the way of writing it in another way. So that means E equals to minus dv upon dr. This is also called the potential gradient, and this is the relation between the electric field potential potential difference, and this is called the potential gradient. Now this electric field, this helps us in this relation, help us to calculate the electric field. Also the relation which we are getting is called the negative potential gradient, and this negative potential gradient is the vector quantity, as we discussed earlier also. Okay, this is the vector quantity, and the relation help us in calculating the electric field. Now after this, let us move to another topic, that is your equipotential surface. Now what is equipotential surface? Equipotential surface is nothing but it is a surface where the potential is same, or in other words we can say the surface over which the electric potential is same everywhere. Suppose we are having a spherical body and plus q charge is kept it in center. The field is created because of this. So if you want to calculate the potential at any point on the surface, so the potential difference will be same everywhere. So suppose we want to calculate the potential difference here, it is same V. Suppose we want to calculate here, it is again V, it is again V, and it is again V. So this is called the equipotential surface. Some important point regarding this potential difference: no work is done in moving the charge on the equipotential surface. That means if we are moving a charge on the equipotential surface, then work is not done. The second point we are having, lines of the force are everywhere at a right angles to the equipotential surface. If you want to draw the lines of force, they are at a right angle. And the third point, two equipotential surface cannot intersect each other. That means if they intersect each other, it means their potential differences varies, so which is not possible. So these are the three important points which you have to remember. After this, we are having the electric potential energy. Now electric potential energy means when we bring two charge closer to each other or away from each other, then we have to do work against their attractive or repulsive force. That means if you are moving a charge away from each other, or when we are bringing two charge closer to each other, in these cases, what we have to do, we have to do the work against the repulsive and the attractive forces of the charge. So this is called the electric potential energy. Suppose we are having two charges, say Q1 and Q2. We are having two charges, one is Q1 and second one is Q2. Q2 is kept at infinity, and what we are doing, we are bringing this Q2 closer to this Q1. Then the potential difference at Q1, the potential difference at Q1 is given by 1 upon 4 pi epsilon 0 Q1 upon R. So what we are doing, we are bringing this charge from infinity at a distance of R. We are calculating its potential difference. Its potential difference created by this charge Q1 is given by 1 upon 4 pi epsilon 0 Q1 upon R. So this is the potential difference. Now we know that V equals to W upon Q. So V equals to W upon Q. So what we have to do, we have to calculate this W. W is the potential energy. So we are calculating W. W equals to V into Q. So W is given by V into Q. So we are calculating W. W equals to V into Q. Put the value of this V. So we have put it the value of V, and this is your electric potential energy. This is the electric potential energy. Now suppose if there are more than two charges, in that case the potential energy will be given, suppose it will be given by 1 upon 4 pi epsilon 0 is common. So we are having different charges. Say this is Q1, the distance between Q1 and Q2 is R12, this is minus Q2, and suppose we are having also Q3 charge. So what we are doing, we are calculating the potential difference. So potential difference is given by this expression. Now the next is work done in rotating an electric dipole in the electric field. So what we have to do, we have to calculate the work done in rotating the electric dipole. So in the electric field, so we have to calculate the work done in rotating the electric dipole in the electric field. Now for this, let us first of all calculate the torque acting on the dipole. Suppose we are having a dipole, say this is the dipole of length 2L, and plus Q and minus Q are the charge at the end. Suppose we have rotated it by an angle theta. So this is the perpendicular distance. So this distance is 2L sine theta. We can calculate this. Now torque equals to force into perpendicular distance. So force is how much? The force is QE on this. So QE 2L sine theta. Now 2QL become P. So 2QL become P. So this is the torque acting on the dipole. Now work done is equals to nothing, but it is equal to torque, or you can say couple into angular displacement. The angular displacement, let us take it as d theta. So couple is how much? PE sine theta. So we have put it the value PE sine theta. Angular distance, let us suppose it is d theta. So we have to calculate the total W. So we have to integrate this. We are integrating it up to the putting the limit 0 to alpha. So we are integrating it. dW will comes out. It's become W only. So PE is constant. So it comes out. So integration of this sine theta will be minus cos theta. So 0 to alpha. So what we have done, W equals to PE will remain PE and minus cos alpha minus cos 0. Cos 0 gives me 1. So minus 1 and minus 1 into minus sign will gives me 1. So we are writing it here. So this is your work done in rotating the electric dipole in the electric field. This is the work done. Now coming to the next derivation. So now let us find out the potential energy of electric dipole in the electrostatic field, or we can say in simply a electric field. Now for this, what we have done, we have taken two charges. Now remember it, we have to calculate the potential energy of an electric dipole. So we are talking about the electric dipole, and this dipole is kept at infinity. We are bringing this dipole inside the electric field. So what happened when we are bringing this dipole inside the field? So it's experienced a force. The force experienced by both the charge, so that means minus Q and plus Q experienced a force. Minus Q experienced QE, and this also experienced QE, but this minus QE travel more distance as compared to plus QE. So the net work done will be equals to the work done by minus Q charge and work done by plus q charge. So work done by minus q charge. So that means we have to calculate the work done by minus q charge, we have to calculate the work done by plus q charge, and we have to add them together. So let us calculate the distance traveled by both of them. So it will be F into 2L plus distance traveled plus distance traveled by plus q charge, and similarly F into distance traveled by plus q charge. This is more distance that we are talking, this is of minus q charge, so we are adding them together. When we open the brackets, then what happened, this distance traveled by plus q charge get cancelled out, it get cancelled, and we are left with minus 2QL E equals to PE. We are left with this. So W equals to U0, that means we can also say the potential energy, so equals to minus PE. In this condition, the dipole remains stable in the electric field. So that means if this is the condition, this is the work done we have calculated, this is also the potential energy. So in this condition the dipole remains stable. But if we rotate it at a particular angle, then W equals to whatever the potential energy plus this work done. So minus PE, this is the potential energy, plus the work done in rotating that. So work done in rotating that we have already calculated. This will be equals to this much. So when we open the bracket, this PE get cancelled, and we are left with this. So this is the final expression. So now the chapter is finished. Now continue with question answer, especially do the long answers. The notes I will send you on the WhatsApp. Thank you very much.